Hello students, welcome to lecture 10 on estimation theory 2. It will cover MVUE and Cramer lower bound. Let us recall the observed random data x1, x2 up to xn are characterized by a joint PDF which depends on some unobservable parameter theta. An estimator theta hat x is a function by which we guess about the value of the unknown parameter theta. So, corresponding to suppose random data, we have a PDF which is characterized by a parameter theta, and estimator theta hat x is a function by which we guess about the value of the unknown parameter theta. An estimator theta hat of parameter theta is unbiased if and only if E of theta hat is equal to theta. So, this is the requirement for an unbiased estimator. A minimum variance unbiased estimator MVUE has the lowest variance in the class of unbiased estimators. So, this is one of the important estimator, that is minimum variance unbiased estimator MVUE, and theta hat, that is estimator theta hat, is called consistent if this probability of any arbitrary deviation goes down to 0 as n tends to infinity. So, this is the definition of consistent estimator. Eventually, as we have more and more data, theta hat will be more and more close to theta. That is the interpretation of consistent estimator. If theta hat is unbiased and limit of variance of theta hat is equal to 0, then theta hat is consistent. That is a simple test for consistent estimator when theta hat is unbiased. The mean square error MSE of an estimator is given by this. MSE is equal to E of theta minus theta hat whole square, and minimizing the MSE is an important estimation criterion. This lecture will revisit the MVUE property and discuss one of the important bounds on the variance of the unbiased estimators, the Cramer-Rao lower bounds. It is abbreviated as CRLB. Minimum variance unbiased estimator, that is MVUE. Recall that variance of theta hat, we define it as E of theta minus theta hat whole square. We can write it as theta hat minus theta, but it does not matter. In both ways we can write. Theta hat is an MVUE if E of theta hat is equal to theta and variance of theta hat is less than equal to variance of theta hat dash, where theta hat dash is any other unbiased estimator of theta. MVUE is also known as the best unbiased estimator because its variance is lowest. Therefore, it is also known as the best unbiased estimator. We will prove one important theorem, and MVUE is unique. Suppose theta 1 hat and theta 2 hat are two MVUEs for the deterministic parameter theta. Clearly, E of theta 1 hat is equal to E of theta 2 hat is equal to theta because of unbiasedness. Suppose variance of theta 1 hat is equal to variance of theta 2 hat, that is equal to sigma square, because both have the same minimum variance. So, let that minimum variance be sigma square. Assume another estimator theta 3 hat, which is given by theta 1 hat plus theta 2 hat divided by 2. Then variance of theta 3 hat will be equal to variance of theta 1 hat plus variance of theta 2 hat plus 2 times covariance of theta 1 hat theta 2 hat, whole thing divided by 4. Now, this expression is less than equal to variance of theta 1 hat plus variance of theta 2 hat plus 2 times mod of covariance of theta 1 hat theta 2 hat divided by 4, because any number is less than equal to its mod value. Now, we will apply the Cauchy-Schwarz inequality, then our expression, this expression will be less than equal to variance of theta 1 hat variance of theta 2 hat plus 2 times square root of variance of theta 1 hat into variance of theta 2 hat, because the magnitude of the covariance of theta 1 hat theta 2 hat is less than equal to square root of variance of theta 1 hat into variance of theta 2 hat. This expression is now equal to sigma square plus sigma square plus this is sigma square, therefore, plus 2 sigma square divided by 4, which is equal to sigma square. Therefore, what we have established that variance of theta 3 hat is less than equal to sigma square, but it cannot be less than sigma square because minimum variance is sigma square. Therefore, variance of theta 3 hat is also equal to sigma square. And if I substitute this value in this expression, then we will get that covariance of theta 1 hat theta 2 hat is also equal to sigma square. So, if there is another estimator theta 3 hat which is equal to theta 1 hat plus theta 2 hat divided by 2, then its variance is sigma square, and this shows that covariance of theta 1 hat theta 2 hat must be equal to sigma square. And now, let us examine this expression variance of theta 1 hat minus theta 2 hat. This will be equal to variance of theta 1 hat plus variance of theta 2 hat minus 2 times covariance of theta 1 hat theta 2 hat. Now, substituting the value, we will get this is sigma square, this is sigma square, and this is sigma square. Therefore, this expression will be equal to 0. That means, variance of theta 1 hat minus theta 2 hat is equal to 0. This implies that theta 1 hat must be equal to theta 2 hat with probability 1. Therefore, an MVUE is unique. Minimum variance unbiased estimator is always unique. The uniqueness of MVUE makes it the most desirable estimator. Now, we will discuss Cramer-Rao lower bound CRLB. The joint PDF or joint PMF of the random vector x, that is x1, x2 up to xn transpose, determines the minimum variance. This joint PDF will only determine the minimum variance of theta hat. Theta hat is a function of these random variables. Let fx theta, that is equal to small f PDF x1 x2 up to xn semicolon theta, that is it is a function of theta, be the joint PDF which characterizes the random data vector x. This function is also called likelihood function. So, this is the likelihood function which is a function of theta, and we denote it by this is the likelihood function. Now, if we take the logarithm capital L x theta, that is the log of this likelihood function, is called the log likelihood function. Now, we define a term known as Fisher information statistics I theta. I theta is the expected value of del L del theta whole square. So, we take the partial derivative of L with respect to theta and then take square. Then the average value of that quantity is a measure of average information, and it is called the Fisher information statistics. Like any information measure, it is also positive, and we can show that it is an increasing function. Cramer-Rao theorem gives a lower bound of the variance of an unbiased estimator theta hat in terms of I theta. So, the lower bound in the variance will be given in terms of I theta. So, we have discussed what is I theta, that is the Fisher information statistics, that is E of del L del theta square. Suppose theta hat is an unbiased estimator of theta and f x1 x2 up to xn theta satisfy the following regularity condition. Likelihood function satisfy the following regularity conditions. That is, theta lies in an open interval d theta. There is an interval d theta on which theta is defined. The support chi, this is defined by x1 x2 up to xn such that this likelihood function is greater than 0. Wherever likelihood function is 0, that support does not depend on theta. So, essentially we will be using a integration, that limit of integration does not depend on theta. Del L del theta, partial derivative of L with respect to theta exists and is finite. So, these three are the regularity conditions. Under the above regularity conditions, variance of theta hat is greater than equal to 1 by I theta, where I theta is the Fisher information statistic. The equality of shear bound, this is the Cramer bound. The equality of shear bound holds if del L del theta is equal to scalar multiple of theta hat minus theta, where C is a constant scalar. It may be a function of theta, but it does not involve theta hat. So, these regularity conditions are fairly general, it is not very restrictive, and under these regularity conditions, Cramer-Rao theorem is variance of theta hat is greater than equal to 1 by I theta. The equality holds when the partial derivative of log likelihood function can be written in this form, C into theta hat minus theta. We will try to prove this theorem. The proof of shear theorem is based on simple calculus and the Cauchy-Schwarz inequality. That is a very important inequality. We have discussed about this earlier, and this inequality is given by inner product. This is inner product, magnitude of the inner product square is less than equal to norm of A square into norm of B square, where equality holds when A is equal to C times B, where C is any scalar. So, this is the statement of Cauchy-Schwarz inequality. In the case of square integrable functions on the real line, we can apply this CS inequality, Cauchy-Schwarz inequality, to get this relationship, that is integration from minus infinity to infinity f1x into f2x dx whole square. This must be less than equal to integration minus infinity to infinity f1 square x dx integration minus infinity to infinity f2 square x dx. So, this is the Cauchy-Schwarz inequality in terms of two functions. So, here this inner product is defined in terms of this integration and norm is defined by this integration. So, that way this is the result we get, and this result we will be using for deriving the CRLB. Also, in the case of two functions, the equality, that is this quantity will be equal to product of this only when one function is a scalar multiple of the other function. Now, we will prove this theorem. Theta hat is an unbiased estimator of theta. This expression, actually this is E of theta hat minus theta must be equal to 0. So, that if we write in terms of the definition, so we will get integration minus infinity to infinity theta hat minus theta into f of x theta dx is equal to 0. This dx is a vector. So, therefore, this integral, actually this is a multiple integral. So, we have suppose n variables x1, x2 up to xn, then this is a n-fold integration. Now, since the limits of integration do not involve theta, we can take this partial derivative inside. Here it was outside the integration, now we can take it inside. Del theta of theta hat minus theta into f x theta dx, that must be equal to 0. This x is a vector here. Now, since this is a product of two functions, we can apply the product rule and we will get integration minus infinity to infinity theta hat minus theta into partial derivative of f x theta with respect to theta into dx. Now, theta hat minus theta will have a partial derivative minus 1, that way minus integration minus infinity to infinity f of x theta dx must be equal to 0. So, this is just applying differentiation, we get this. So, we will take this quantity right hand side, so that way it will become positive, and then also I note that this integration is equal to 1. Therefore, this quantity integration theta hat minus theta into del del theta f of x theta dx, that must be equal to 1. This result is very important for us. Now, we have established that integration minus infinity to infinity theta hat minus theta del del theta f of x theta dx, that is equal to 1. This is, suppose we call this expression as 1. Note that this partial derivative del theta of f x theta, we can write in terms of log likelihood function like this, del theta of log of f x theta into f x theta. So, this will be same as this quantity, because 1 by f x theta will come, and that and this will get cancelled. So, that way this expression can be rewritten as this. So, that del theta of f x theta is same as del l x theta del theta into f x theta. So, this is a one important derivation. Therefore, this expression 1 can be rewritten as now integration minus infinity to infinity theta hat minus theta into del l x theta del theta into f x theta dx is equal to 1. So, this is the modified form of this equation. Our aim is to apply the Cauchy-Schwarz inequality to the left side of this expression. So, that way we first square it, this expression if I square, then also this will be equal to 1. Now, we have to write it as a product of two functions, and since this quantity is greater than equal to 0, we can take the square root, and that way we can write it in terms of two functions. One is theta hat minus theta into root over f x theta, and other one is that partial derivative of l x theta into square root of f x theta dx. So, that way we have two functions now. So, this expression is rewritten as integration minus infinity to infinity, integration from minus infinity to infinity of theta hat minus theta into root over f x theta into del theta of l x theta into root over f x theta dx whole square is equal to 1. So, we have now product of two functions. Suppose if I call this as A, this is, suppose this is equal to A vector and this is B vector, this part is B vector, this part is A vector and this part is B vector. Then we can apply the CS inequality. So, therefore, this is the inner product of two functions square. So, that way this square must be less than equal to, if I consider the norm of individual function, this will be integration minus infinity to infinity theta hat minus theta whole square. This is theta hat minus theta whole square, and this is square root of fx theta. Therefore, squaring we will get f of x theta dx. So, this is first term, first norm square, and norm of the second function square will be integration from minus infinity to infinity del L del theta whole square into fx theta dx. So, by definition, this is the variance of theta hat, and this part is the Fisher information statistics. So, variance of theta hat into I theta. So, this because this expression is equal to 1, therefore, 1 must be less than equal to variance of theta hat into I theta. So, from this now we will get that variance of theta hat is greater than equal to 1 by I theta. So, thus we have variance of theta hat is greater than equal to 1 by I theta. The equality will hold when one of the function, that is suppose first function del L x theta del theta into root over f x theta, that must be multiple of the other function c times theta hat minus theta into root over f x theta. That is the condition for equality in the case of Cauchy-Schwarz inequality. So, since this quantity, actually we want this to be greater than 0 in the region of support, that is the regularity condition. Therefore, we can cancel these two quantity. So, what we will get? We will get this equality will hold when del L del theta is equal to c times theta hat minus theta. This is the condition for equality, where c is independent of theta hat. It is a scalar actually, and may be a function of theta. C may be a function of theta, but c does not involve x or c does not involve theta hat. Now, to find c, if we take the square of this and take the expectation, then E of del L del theta whole square will be equal to c square times E of theta hat minus theta whole square. So, that way c square will be equal to this divided by this, E of del L del theta whole square divided by E of theta hat minus theta whole square. This is the variance and this is the information statistics. So, that way I theta divided by variance of theta hat. So, c square is equal to I theta divided by variance of theta hat. So, this scalar c is given by this. Now, we know what is I theta, but there is a better expression algebraically for I theta that we can derive now, that is integration of f dx is equal to 1 join PDF likelihood function integrate with dx must be equal to 1. This implies that partial derivative of this quantity must be equal to 0. Again, under the regularity conditions, we can take this partial derivative inside. Therefore, del theta of f x theta dx integrating from minus infinity to infinity must be equal to 0. Now, this we can write as this quantity. This quantity now we can write in terms of log likelihood function. So, integration minus infinity to infinity del L del theta into f dx, that must be equal to 0. This is the expression we get from here just by writing this expression in terms of log likelihood function as we did earlier. So, now what does this expression implies? That expected value of the partial derivative of log likelihood function is always equal to 0. This is also one important result. But we are interested to the second partial derivative. Therefore, we will again take the partial derivative of this expression That way we will get, because now it is a product of two functions. So, if we take the partial derivative with respect to theta again, and of course, we assume that these partial derivatives exist. So, second order partial derivative of L with respect to theta into f x theta, that is the first term, plus again this term is into partial derivative of this. So, now this again we will be writing in terms of log likelihood function. That way we will get this squared here into f x theta dx. Okay. So, from this expression now, if I consider this is nothing but the expected value of this quantity, and if I consider this is the expected value of this quantity. Okay. So, that way what I get is that because I know that expected value of this quantity is the information. So, therefore, I theta is equal to E of this quantity, and that must be equal to if I take this quantity right hand side, it will be negative. So, that way minus E of del square L del theta square. So, minus E of del square L del theta square. So, that way this information statistic I theta can be expressed in terms of this second order partial derivative, that is the average value of the second order partial derivative with a negative sign, and compared to taking the square of the partial derivative and then expected value, this expected value is easier to compute. So, therefore, we can write Cramer-Rao lower bound for variance of theta is equal to 1 by I theta, that we have already established, that is equal to minus 1 by E of del square L del theta square. So, that way we can simplify this expression, and also we have established that CRLB is reached if this first order partial derivative del L del theta is equal to C times theta hat minus theta. So, this is the Cramer-Rao lower bound given by this expression, and this CRLB is reached if this likelihood function satisfy this relationship. Let us make some important remarks. CRLB specifies the optimal bound that we can hope to achieve in terms of the variance of an unbiased estimator. It is an optimal bound. However, this bound may not always be achieved, that is we may not reach this bound. If theta hat satisfies CRLB, suppose we have an estimator which reaches CRLB, then theta hat is an MVUE, because its variance will be minimum. We cannot have variance lower than that. So, theta hat in that case is an MVUE and also called an efficient estimator, that we have defined earlier. We have derived CRLB using continuous random variables. So, because we derived assuming joint PDF, but the same can be derived for discrete random variables by replacing the PDF by PMF and using the same regularity conditions. So, that way CRLB is more general than what we derived here. It is true for both continuous and discrete random variables. Further, suppose x1, x2 up to xn are IID, independent and identically distributed. Then suppose if I consider only one random variable, I1 theta is equal to E of, by definition, partial derivative of likelihood function whole square, and that is also equal to minus E of del 2 del theta square of log likelihood function. So, that we have already established this. Therefore, if there is only one variable here I1 theta, I can write like this. Now, I theta is log of, that is we have to take the del 2 del theta square of log likelihood function of n random variables. So, now this joint PDF we can write in terms of marginal PDFs like this, as a product of n marginal PDFs. So that way this will be del 2 del theta square of log of product of n marginal PDF f xi theta. And this product now we can, because it is logarithm of the product, we can write it as the sum of logarithm. So that way del square del theta square of summation I going from 1 to n log likelihood functions ln f xi theta. Now this we can take inside this, so that way, and all are identical, all random variables are identical, therefore they will have the same information statistics I1 theta, and there are n such variables, therefore it will be n times I1 of theta. So that way, if xi's are IID, independent and identically distributed, then the Fisher information statistic for these n random variables is equal to n times the Fisher information statistic for single random variable. So that is the result for IID case. Otherwise, if only independent, then we have to add all this, all information we have to add. That is the additivity property of information. We will give one example. Suppose x1, x2, xn are IID Gaussian with known variance sigma square and unknown mean mu. Suppose mu hat is equal to this summation xi I going from 1 to n divided by n. This is the sample mean, which is unbiased, we have already proved. Find shear bound and hence show that mu hat is an efficient estimator. So f is this is the likelihood function, log likelihood function. For single variable it will be like this, we are taking the logarithm, therefore it will be minus of this, because here 1 by is there, and then minus half of x1 minus mu by sigma whole square. Now we have to take the second partial derivative. So only this term will involve x mu, therefore we take the first partial derivative and then again the derivative, we will get this is equal to minus 1 by sigma. And therefore second order partial derivative del 2l del mu square will be equal to minus 1 by sigma square, because this expression only involves mu. If we take twice derivative, then it will be, so mu will not be there, so it will be simply 1 divided by sigma square. So therefore I1 theta, if I consider only one random variable x1, then its information will be equal to 1 by sigma square. And since xi's are IID, therefore I theta will be n times I1 theta, that is equal to n by sigma square. Therefore CRLB, Cramer lower bound, is equal to 1 by I theta, that is equal to 1 by n by sigma square, that is sigma square by n. So this is the Cramer lower bound. Same example we are considering. So now again we consider this likelihood function, this is given by this, and if we take the log likelihood function is given by this. And now let us take the first derivative, first partial derivative. So this quantity will be equal to, that is del L del mu will be equal to summation, because we will take the partial derivative of this, 2 and 2 will get cancelled. So that way summation xi minus mu by sigma I going from 1 to n, that is the partial derivative of the log likelihood function. So now here sigma is there, this sigma I will take out and I will write n here and divided by n here, so that this expression can be simplified as n by sigma into mu hat minus mu. So we have seen that del L del mu, that is the first partial derivative of log likelihood function, is a product of one constant term n by sigma into mu hat minus mu. Therefore, according to the equality condition of Cramer-Rao theorem, mu hat will reach CRLB. So, because this partial derivative is product of this factor mu hat minus mu and a scalar, therefore, mu hat reaches CRLB, and hence mu hat is an efficient estimator. Let us summarize the lecture. The uniqueness of MVUE makes it the most desirable estimator. So, that uniqueness we established. Lx theta, that is equal to log of the likelihood function, is called the log likelihood function, which characterizes the observed data. I theta, that is Fisher information statistic, that is equal to E of del L del theta square, and also related as I theta, also we express it as equal to minus E of del square L del theta square. Cramer-Rao theorem, that also we establish for an unbiased estimator theta hat under certain regularity conditions, variance of theta hat is greater than equal to 1 by I theta. I theta is given by this Fisher information statistic. Thus, CRLB, Cramer-Rao lower bound of variance of theta hat is 1 by I theta, that is the bound, and that is equal to minus of 1 by expected value of del 2L del theta square. CRLB is reached if this partial derivative of log likelihood function is a product of C and theta hat minus theta, where C is a constant. If theta hat reaches CRLB, then theta hat is an MVUE. So, that is very important. So, our search was for an MVUE, and if theta hat reaches Cramer-Rao lower bound, then it is an MVUE, and therefore, it will be an efficient estimator. Thank you.